All right, let's dive right in. Today, we're getting down to the absolute heart of modern electronics. We're going to talk about the tiny, brilliant component that makes your phone, your computer, pretty much everything with a circuit board actually work. It's called the PN junction, and it all starts with a really simple question. So think about this for a second. We know electricity flows, right? But what if you wanted to tell it where to go? What if you needed to build a perfect one-way street for it where it could only ever travel in a single direction? How in the world would you even start to build something like that? Well, believe it or not, the answer begins by bringing two very special but totally different types of materials together. We're talking about semiconductors. And you can just imagine it as two distinct worlds, each with its own special properties, about to collide. So on one side, you've got what's called an N-type semiconductor. Just picture a place that's overflowing with free electrons, just buzzing around, looking for somewhere to go. Then, on the other side, you have the P-type semiconductor. This place is the exact opposite. It's full of what we call holes, which are basically perfect little parking spots just waiting for an electron to fall into them. And when you bring these two materials together really carefully, that surface where they touch, that's the PN junction. It's right there at that exact seam where all the physics magic is about to unfold. Because the very instant they touch, bam, something completely wild and unexpected happens right at the border. An invisible wall, a great divide, just pops into existence all on its own. And this barrier is really the key to everything. So what's going on in that split second? Well, it's this crazy fast chain reaction. First, all those free electrons on the N side see the empty holes on the P side, and whoosh, they rush across the border. Then, they fall into those holes, and they basically cancel each other out. But, and this is so important, this leaves something behind. The atoms on the N side that lost an electron are now positively charged, and the atoms on the P side that gained one are now negatively charged. And the end result of all this frantic activity? You get this thin little strip right at the junction that has no free electrons and no free holes. It's kind of like a neutral, no man's land for electricity. And this area has a name, of course. We call it the depletion region. Those layers of positive and negative ions create an electric field, and this field acts like a barrier, a force field really, that pushes back and stops any more electrons from trying to cross. The flow just stops dead in its tracks. Now, this wall, it's not just some abstract idea. It has real, measurable strength. For silicon, which, isn't pretty much everything these days, you'd need to give it a 0.7 volt push to get any electrons past that barrier. We call that the barrier potential. And that number isn't set in stone. If you were using a different material, say germanium, that barrier's a little weaker. It only needs about a 0.3 volt push to get through. Okay, so we've got a wall. Now what? How do we actually control it? And that brings us to the really cool part, the solution. We can actually control this barrier. We can open the gate, and we do it by hooking up an external voltage, like from a battery, in a very specific way. This whole process is called forward biasing. So with no battery, that barrier is just sitting there, being a wall, blocking everything. But to forward bias it, check this out. You connect the positive terminal of the battery to the P side and the negative terminal to the N side. What you're doing is literally pushing the holes from one side and the electrons from the other side right towards that barrier. And wow, the effect is immediate. The external push from the battery just overwhelms the barrier's own internal field, causing it to shrink down. The resistance of the junction just plummets, and boom, the gate flies wide open. Current starts flowing through the circuit. We've just flipped the switch to on. Okay, so if that's how we open the gate, you can probably guess what happens if we do the exact opposite. What if we flip that battery around? Well, that's called reverse biasing, and it's how we slam the gate shut and lock it tight. For reverse biased, we connect the negative terminal to the P side and the positive to the N side. So now, instead of pushing everything towards the junction, we're actually pulling all the electrons and holes away from it. And what does that do? It makes that barrier even wider, even stronger than it was before. The resistance of the junction just goes through the roof, and the gate isn't just closed, it's sealed. Essentially, no current can get through at all. We flip the switch to off. So let's just take a step back and appreciate what we've just created. Just by changing how we connect a battery, we've made a component that has a kind of superpower. We've built an electronic switch with 0 moving parts. And this amazing little thing is called a diode. Let's boil it all down real quick.
Under forward bias, the barrier shrinks, resistance is low, and current flows. Under reverse bias, the barrier grows, resistance is super high, and current gets blocked. On and off. It really is that simple.
And there you have it. This confirms we did exactly what we set out to do. We successfully built a unidirectional gate, a perfect one-way street for electricity. Current can go one way, but there is absolutely no way it's going back the other. And that leads to the most mind-blowing part of all this. This simple component, this microscopic on-off switch, is the fundamental building block. It's the atom of all digital logic. Every computer chip, every LED, every solar panel relies on this exact principle. It's the simplest idea that allows for immense complexity. So the real question isn't what you can build with it, but what can't you?